So we know the Hamiltonian for a hydrogen atom. Really, it's just the Hamiltonian for the electron. So we've got the Hamiltonian is the kinetic energy of the electron plus the potential energy for the electron. And the potential energy we know is the Coulomb potential, and we know the kinetic energy. So in the position basis, it's going to look like this. Well, that's the radial coordinate. So what we're going to choose is our trial wave function. Obviously, if we have a very large radius, then it's going to be higher energy than if it's closer to the proton. So at some level, if we have our wave function as a function of radius, we want our trial wave function to be dying off as it goes off to large r. So it could be a bump, something like that. It is in fact, or it could be a Gaussian, something more like this. Or it could be an exponential. It is in fact an exponential, but let's pick something a little bit different so that we get at least one example where we don't happen to guess the right answer. Let's make our trial function something that looks like this one here, where we've got maybe an exponential times a radius. So it'll be an exponential. I'll have to have some kind of rate of decay, so we'll make that a parameter a, but we'll also have an r here. And so our wave function is going to be a function of r, not theta and phi, because we're assuming it doesn't depend on those, and our coordinate a. Now we need to include a normalization constant. Remember, when we're integrating over 3 dimensions in radial coordinates, in polar coordinates, we've got to break this down into a radial part, which goes from 0 to infinity, and we also have an r squared. We have a theta term that goes from 0 to pi, and also has a sine theta. And we have a phi component that goes from 0 to 2 pi that does not have anything. You know, the units of that are correct. If we didn't have the r squared, we wouldn't have the right units. That would definitely be wrong. And you just have to remember the sine theta. Now, our particular wave function doesn't depend on theta and phi, and so we can just perform those integrals. In fact, you may know that the answer to that integral is 4 pi steradians. We'll check that when we go to our Mathematica, but that's just a 4 pi. So now you have r squared times the square of that. We do that integral in Mathematica. So here's just checking that we've got 4 pi steradians. That worked fine. We'll define our wave function, and so we've got our a is going to be our normalization constant. And now if we calculate, remember we've got the 4 pi there, if we calculate the norm of that, we get this. So if we want that to be 1, we have to set a to be 1 on square root of the rest of it. So now we've got our trial wave function and it's normalized. Now we need to actually calculate the expectation value of the Hamiltonian. Now we've obviously got 2 terms. We've got this grad squared term and we've got this term. Now this term is kind of the simplest. So the expectation of 1 on r will have a minus e squared on 4 pi epsilon naught out the front of it, which is just an exponential integral we can plug into Mathematica and pull the answer. So here I've got the exact thing that gave me the norm, and here I've got almost exactly the same thing, except I've got an r instead of an r squared because I've had to divide by r. I've still got my 4 pi because I'm still actually integrating over those, and this time I'm going to set my big constant to be equal to the thing that gives me the right norm. Crunch, crunch, and there's my answer. And here I remember to put my 4 pi in for my 4 pi steradians, and then I get my 1 on 2a. And so when I multiply by e squared on 4 pi epsilon naught and a minus sign, I'll actually get that contribution to the energy. The other thing I need to know is what is the expectation value of this grad squared? And obviously I have these coefficients as well. Now grad squared in polar coordinates looks like this, which pleasantly, most of this is 0 because our wave function has no phi dependence, so all that is 0, and it has no theta dependence, so all that is 0. And so we just have this term, which again we can crunch. We could put the Hermitian conjugate there, but it's real valued, so that doesn't help. That operator there, and then our wave function again. And again, we'll do this by Mathematica. So now we have a very similar thing. We've got a 4 pi there. We've got our ddr squared of the derivative with respect to r and the psi. And all of this assuming that we've got the correct norm. And there's our answer. Very simple. One thing to check, do I have the right units? This is the expectation value of something that's a double derivative, so it should have inverse length squared. So a should be units of length, as we can see. So therefore, yes, that's the right units, and I'm happy. And again, I'll remember my factor of 4 pi. One of the real problems with factors of 4 pi, 2 pi, and pi, and 2, is that they don't have any units, so it's very easy to miss them. Same with minus signs, although we have a little bit more sanity with that. So there we go. Now we put it together, and we have a function of A. And we can see again that we've got a competition between two terms, and so there'll be an optimum. So we take the derivative with respect to A, and we force that to be 0. And so our value for A is that, which happens to be 2/3 of the Bohr radius. So the Bohr radius is what the actual wave function is, and so that A would have been an A0 in that case. And this isn't quite the same, and it's not quite the same because we're minimizing the energy for this shape wave function, which is different to just a straight exponential. And what is the energy for this optimal value of A, which minimizes it? We just plug this into here, which of course, after a bunch of algebra, gives us, which is a large number of things. In fact, it's almost exactly the same form as the correct answer. So the correct answer is of that form, but 4/3 as big, i.e. 4/3 as deep. So the correct answer is of course lower. This is an upper bound for the energy. But why did it have all the same functional dependence on E, M, epsilon naught, and H bar? Again, dimensions, of course. The only thing that could change are these 3's on 128's and possibly pi's, which is why we've got a nice simple factor. And so that's an upper bound for our energy at the ground state of hydrogen.